Nature has always worked with ease. Millions of gallons of water are transported thousands of miles, 24 hours a day, 365 days a year. This water is moved across deserts, over mountains, and even between continents. It is all done without pumps, electricity, or the need for fossil fuels. The entire planet, almost 200 million square miles of it, is run with solar energy. Nothing is wasted, everything is recycled. Yet when it comes to designing our buildings, we take it for granted that our structures need mechanical heating and cooling systems. We take it for granted that energy is piped and wired into our homes and offices, and that we have an electric bill every month. We take it for granted that we must pump oil and gas from the ground, that power plants pollute, that our cars pollute, and that our skies are clouded with smog. It is simply the price we must pay for the convenience our technology offers. Or is it? What if, through changes in our building designs, we could start moving towards extremely energy-efficient buildings that generate much of their own pollution-free power? What if these buildings actually saved us money in their operation? What if your home generated more power than it needed and could actually sell this power back to the utility company? These buildings are not concepts for tomorrow. They are being built today, and implementing this kind of change may be easier than you think. This is working with instead of against nature. This is building with awareness. Hybrid structures are constructed using a wide variety of materials. In Corrales, New Mexico, just on the outskirts of Albuquerque, designer Ted Owens designed and built his own house using both conventional and progressive building techniques. It balances the best of both worlds by generating electricity with high-tech photovoltaic panels on the roof, while using low-tech straw bale and adobe walls for stabilizing interior temperatures. Despite the structure's small footprint of 800 square feet, each room feels spacious and bright. By building the home no larger than was needed, money could be put into aesthetic elements instead of square footage. Detail and design were as important as energy efficiency. The choice of materials was based on their visual appeal, ease of use, energy efficiency, and the amount of embodied energy. That is, the amount of energy it took to actually manufacture the material. Windows were positioned so that natural light would filter into the entire living space from at least two sides of each room. In addition, they were carefully placed to ensure good ventilation and also to direct the eye to the outdoors from key vantage points. This design technique is useful in opening up small spaces visually, thereby making the rooms appear larger than they really are.
I built this house as kind of an experiment. It was to see what it was truly like to work with sustainable and green materials, what kind of difficulties there might be in the process of working with them, and what worked really well and would be very easy for any person to incorporate into their own structure if they happen to be building one. The opportunities for combining low technology with the high technology, to me, it's really exciting. I mean, you have these materials like straw and mud, and you're combining them with very high-tech materials like silicon photovoltaic cells on the roof that are converting sunlight into electricity. One thing I found that was quite nice and quite a nice balance to building with sustainable materials is that there's a beautiful aesthetic to it. It's a very soft aesthetic. It's very different. Walls are straight, but not totally straight. There's kind of a handmade quality to things. Unlike wallboard and frame construction, which is what the majority of all houses are made out of today, you have to be absolutely precise. You've got to have 90-degree angles. Your wallboard has to be flush with the next piece that it butts up against, or else the whole aesthetic falls apart. I mean, you get cracks and bumps, and it just doesn't look right because you're dealing with a very hard, angular material. With natural materials, you can actually form these walls with your bare hands. You kind of warp things into position because it's all kind of pliable and flexible like clay. I mean, the adobe, literally, you can stack the adobe bricks, put in subtle curves. The corners you can actually come in after the fact and sand them to nice radiuses, and you don't have to be stuck with the hard edges. Since my background is as a designer, obviously the aesthetics had to play a very important part of this. And I think this is actually something that is sometimes forgotten or missed in sustainable design. That if the house is not aesthetic, or the building or whatever it is you're making, it's probably not going to last as long. You need to have structures that feel good, that look good visually. And this is something I think is missing quite often in our cities and towns today, particularly in houses. I think one of the biggest challenges if you're going to build your own house out of green materials, it's the research stage. There's always going to be compromises. There's no one material that is always going to be better than one over the other. Straw bale is a great material. However, if you have to import it 1,000 miles by truck, maybe that isn't quite as sustainable as something else that might be available in your area. The other material I chose that was very important to use for thermal mass on the inside was adobe. Adobe in this area in New Mexico is very easy to obtain. It's locally produced, and it's a very easy material to work with. The wall covering in this house is actually mud, and I mean pure mud right out of the ground. For large dimensional lumber, that is, anything over 6 by 6 inches, we always used recycled wood and made an effort to feature it in the construction. By doing this, we were able to have the aesthetic advantage of heavy timbers without cutting down old-growth trees. I obtained this lumber from either salvage yards or local renovation projects being done by friends.
Winter temperatures here can dip into the mid-teens at night and only reach the mid-40s during the day. More than half the heating needs of this home can be supplied by taking advantage of sunlight alone. Through careful planning and design, we can take full advantage of sunlight and temperature swings, having them work for us instead of against us. Even small differences in construction techniques can lead to great improvements in energy efficiency and savings. For example, by simply rotating the angle of the structure a few degrees so that the majority of the windows face south, the homeowner can potentially save thousands of dollars in energy costs. As the low winter sun moves across the sky from east to west, solar energy sweeps across the interior surfaces of the home through the south-facing windows. Sunlight is energy, and when it hits the darker-colored walls and floor, this light energy is converted into heat, just as the interior of your car warms up on a sunny day. The heavy mass of the adobe walls and the concrete floor then act as a storage medium for this heat. This is called thermal mass. These heavy materials warm up under the sun and then slowly release the stored heat back into the room during the night. It is a simple and elegant system. With all its thermal mass and insulation, the interior temperature rarely changes more than 3 degrees during a 24-hour period, even when the backup mechanical heating system is not being used. In cold weather, windows on the north side will only drain the home of heat. Therefore, they are kept small and to a minimum. They are just big enough to add some interior light and to assist in summer cross-ventilation. The west side of the house has only one window. Any glass in this wall will allow the late afternoon summer sun to overheat the inside of the house. Two openings at opposite ends of the ceiling create cross-ventilation to eliminate trapped heat. In Albuquerque, the temperature on summer days will average around 90 degrees. Evenings, however, are pleasantly cool. This cooler night air, along with the thick adobe interior walls and the highly insulative exterior straw bale walls, will keep the home comfortable during the day. This is accomplished by opening windows at night in order to cool down the thermal mass. In the morning, the windows are again shut in order to keep out the heat of the day. The east side has 3 small windows. A portal shades this side of the house, so there is a bit more flexibility in determining the size and number of windows here. The kitchen window is large enough to take advantage of the scenic mountain view, while the loft and bathroom windows are used primarily for ventilation and light. As with any structure, the design starts on paper. On paper, both the aesthetic and solar aspects can be manipulated and evaluated. Spending time in the sketch and design stage is one of the most important phases of constructing a home.
This is an overall floor plan of the house as we're going to build it. And as you can see, all of the exterior walls are made out of straw bale. Those are 18 inches thick, and this gives us very high insulation in the exterior walls to keep the heat of the summer out and the cold of the winter out. All the interior walls of the house are adobe. This is indicated by the orange areas. It's very important to get as much thermal mass, which means thick, heavy walls made out of something like adobe or stone, within your outer shell of highly insulated walls. Thermal mass on the inside, straw bale on the outside is the best combination for reducing your heating and cooling needs. Sometimes even in solar houses, they leave out the interior thermal mass walls, which is actually very inefficient because these interior walls are not only releasing stored heat in the winter, but also absorbing excess heat in the summer. This is the south side of the house, and here's our entry through a portal, then through an entry hall and into the main living area. This section here is the dining room area, and then there's an 18-inch rise in the floor that makes up the living room area. Either section alone would be too small for an actual living space, but since they're softly divided with a 3-foot-high wall and a bookshelf, the overall area feels very generous in its size. Kitchen is here, and then on the north side, where we're not using it as much and so heat isn't quite as important, we have a storage closet area back here, a utility room that includes a washing machine, and then this section here is the bathroom. And right off the portal, we have the mechanical room. And this room contains tankless hot water heater, a pressure tank for the well, and also a standard hot water heater which heats the radiant floor heat. Now this is divided by a frame wall, one of the only frame walls within the house, and this wall is framed because we're running plumbing through there. Note that the mechanical room is directly adjacent to both the bathroom and the kitchen sink. This makes for very short runs of the hot water line to both the bathroom sink, the shower, and the kitchen sink. This saves both water and energy in heating the water. The battery room is also on the north side with access only from the outside. And this area here, above the kitchen and the entry hall, this is a loft. This is a cutaway view of what the house looks like if you actually just cut it right down the center of the house. You can see the thickness of the 2-foot thick adobe wall that divides the living area from the closet area. You can also see the thickness of the truss area that will have insulation in it. This also shows the thickness of the straw bale wall, which you can see here, which is about 18 inches wide. Here's the glass window on the south side. Now in the winter, the sun is very low on the horizon, and this line here shows how the winter sun comes just in under the eave of the roof, underneath the window, and goes about 3/4 of the way into the living area of the living room. So this whole area here is collecting solar energy. Now in the summer, you don't want any direct sunlight to come in, and the way the sun actually works, in the summer, the sun comes in from a very high angle from up above. So in the summer, the sun angle is coming from about here, and therefore there's no direct sunlight at all coming into the house. Winter sun angle, summer sun angle. Solar energy entering the house, solar energy totally cut from the house. I'm a designer professionally and not really a builder. So I got to admit it was very intimidating to come up with the idea that, okay, you're going to build your own house. Before I started this structure, I think the largest thing I'd ever built was probably a fort in my neighbor's backyard when I was 5 years old. So there's definitely busting through that mental barrier of just getting going on the project, and you build until it's done.
This home will be 100% owner-built and contracted. Among the core crew members, in addition to Ted, will be his father, Al Owens, a retired electrical and mechanical engineer in the communications satellite field. Although he is quite skilled using power tools for home repair projects, this will be his first experience actually building a house from the ground up. Tom Carson, a friend and neighbor, is just finishing his degree in architecture at the University of New Mexico. Tom will act as the key construction consultant and will work part-time through all phases of building the house.
Okay, good.
Although he has been very involved in conventional wood frame construction, this will be his first experience using alternative building materials.
No, I know, but...
Mark Steinkamp is also an architecture student with a background in conventional construction. He will help out as needed during the framing, roofing, and straw bale phases of the project. This will also be his first experience with alternative materials.
The first thing we built was a workshop, which will be in lieu of a garage. This allowed us to experiment with building materials and techniques, which would be later used in the construction of the house itself. These included the rubble trench foundation, adobe walls, and cob infill on the gable ends.
Once the house is sited into position, trenches are dug in preparation for the foundation, and straw bales are delivered to the construction site. The production of cement generates approximately 7% of all greenhouse gases on the planet, a fact not known to most people. Therefore, how and where this material is used in the building of this house will receive careful consideration. In some cases, it will not be used at all, but instead be replaced by a more sustainable alternative. In cases where concrete is appropriate, it will be used judiciously, serving whenever possible multiple purposes of structural component, aesthetic element, and thermal mass. Foundations use a substantial amount of concrete, particularly when the foundation is 18 inches wide, the width of a straw bale wall. A rubble trench foundation reduced the amount of concrete used here by more than 50%.
One way of making a foundation for a straw bale house is to dig a trench that is about 18 inches wide, the width of a straw bale, and as deep as the frost line. Let's say it's 20 inches in your area. Code requires that the foundation be insulated, so we placed 2 inches of foam on the outside edge of the foundation. This slows down the heat loss through the foundation. This entire area is then filled with concrete. You end up with a huge block of concrete that is just total overkill for this type of wall. We are going to use a rubble trench foundation. It is also extremely strong and reduced the amount of concrete by over 50%. The 2 inches of foam insulation is still installed on the outside, and a French drain is then placed at the bottom of the trench. This is a 4-inch diameter perforated pipe that is required by code. Now comes the good part. Most of the trench is filled with 1.5 to 2 inch broken stone. This is why it's called a rubble trench. The rubble is what replaces the concrete. Only the top 8 to 10 inches of the foundation will be a grade beam of concrete. There are 2 pieces of rebar that are also required by code. Now compare the 2 foundations. This solid block of concrete has been reduced by over half in the rubble trench foundation, without any reduction in structural integrity.
Now that our trenches are dug, we can start laying the perimeter drain, which runs around the entire perimeter of the foundation. And what it's made out of is basically just a 4-inch perforated pipe. And this will allow any water to drain out if it were to get into the foundation system sometime in the future. What happens is it goes through the perforations here, and then we have it a slight slope draining out to the lower side of the property.
This is the 2-inch thick foam that is on the outside of the foundation. It has an insulation value of around R10. In this foundation, it will serve 2 functions. Number 1, it will act as insulation for the foundation itself, and number 2, it will also serve as the outside form for the concrete pour.
As you can see here, we've laid the foam about 2 inches higher than our string here that indicates the top of where we want our concrete pour to be. When we have the foam in place, we'll then go back and cut the foam off at the string level, and then this will act as the retainer for concrete on this side of the perimeter beam and also act as our screed so we can smooth off the top of the concrete after we pour it.
String that is attached to the batter boards is used to precisely position the foundation, including the finish height. It is much easier to trim the height of the foam later on, instead of trying to position multiple pieces of foam to the perfect height from the very beginning.
To keep the foam aligned to our string markers, we're using 1x2s with a couple of nails in the end. And those are used to warp the foam into position and hold it there. The line that Al is drawing will indicate the top of our crushed rock, and concrete will be poured above that line.
As gravel is placed on the inside face of the foam, dirt is placed on the outside at the same rate. This ensures that the foam does not bow in or out, and it keeps it running in a straight line with our string guide.
If the trenches had been dug to the perfect width, the foam could have been affixed smack up against the dirt wall of the trench, and this would have eliminated the need for some of this backfilling with dirt. It's very important to tamp down the gravel and the dirt to ensure that it is thoroughly compacted to prevent settling in the future. Now that we're completing our foundation system, we got to start thinking about plumbing. This is called the drain, waste, and vent piping for the house, which will ultimately end up being underneath the slab. We've dug down up to 30 inches for the toilet piping here, and this pipe here, which runs parallel to it, is for the gray water. This will take care of the shower, sinks, and washing machine.
Once the line is outside the perimeter of the house, the gray water pipe passes through a diverter valve that will permit this water to be channeled off to a future gray water recycling system. At the time of construction, gray water systems were not permitted in New Mexico. I assumed that the law would someday change, and they did. Now gray water systems are permitted in the state, and hooking up the system will be quite simple since all of the valves are already in place. By having an accessible diverter valve, the gray water can be made to flow back to the septic system when desired. Once past the diverter valves, both the black water and gray water lines merge into one and then proceed to the septic system.
We're at a point now where we have to install all the underground utilities before we can pour the foundation and slab. And that'll include conduit for both the power, the telephone, and cable TV. So what we're doing here is we've made a maze of trenches around our building project here, routing everything to its proper location. As you can see, the conduit runs underneath our foundation, including the perimeter foam, and into a trench.
We used a machine called a ditch witch for digging most of the trenches for the conduit and plumbing. It makes a trench about 5 to 6 inches wide, which is just wide enough to drop in the pipe very conveniently. We used copper pipe for all of our freshwater plumbing. This trench contains 2 freshwater lines using copper pipe, in addition to a plastic line that will carry water from the cistern for non-potable uses within the home.
These are the forms for the foundation for the adobe walls that would be the interior walls of the structure. They're constructed out of 1x8, which I acquired from a friend's renovation project. So we're using recycled wood for the forms, since when they're poured with concrete, they get pretty much thrashed and useless for much else. This string here is indicating the top floor level of the foundation, and the top of the interior wall foundation is at the exact same level as our floor. We'll lay the adobe bricks directly on top of this. The next step is to install the rebar in the concrete portion of the foundation. And steel support chairs are used to raise the level of the rebar a couple of inches off the ground. And this ensures that the rebar will be suspended within the concrete and not laying just directly on the ground. And note that the rebar overlaps at the joints and crosses from the inside to the outside at the corners. And this is done for additional strength. The foam will now be marked to the height of the finished pour of the concrete, and this is done by using a very simple device called a water level.
It's a pretty handy little device. Basic business.
It's nothing more than a long tube filled with water. Due to gravity, water at one end of the tube will always be at the exact height as it is on the other end. From our survey stakes, we pick a point that indicates the proper finish height, and this becomes our master reference point. The other end of the level is then taken around the foundation, and this same height is marked there as well, since the water is always level. It's a real low-tech system that's very simple and accurate. While moving the level, each end is capped to prevent the water from spilling out the other end when one end is higher than the other.
Okay, capping.
Capping. Cap on.
Next, Tom and Al will snap a chalk line to connect the elevation marks on the foam. Some 2x4s can be clamped to the foam to act as a guide while cutting the foam with a handsaw. As you can see here, we're using straw bales for the inside form of the concrete. Once again, this saved on wood since we had the straw bales on hand. Either metal stakes or adobe bricks were used to keep the bales in place. It's then just a matter of nudging the bales to the 18th inch width of the foundation.
Good.
Tar paper is then attached to the bales so the concrete will not bond to the straw, and nails were used to pin the paper to the bales. The final step was to hammer number 4 rebar into the stone rubble. This vertical rebar will extend high enough to go through 1.5 bales of straw for the finished wall. There are 2 rebars in each bale, and the aluminum cans you see here are strictly for safety so that no one gets cut by the rebar during construction. So that's it. We order the concrete and we're ready for the pour.
go.
We had to use a wheelbarrow in a few places when the chute from the cement mixer would not reach.
And now what we've done after doing an initial screeding to the right depth, we're coming in with a trowel and smoothing it out, and we're going to drop in the anchor bolts for the post supports. The foam is at the proper height. The straw bales are a little too high, so we're just using a 2x4, resting it on the foam and screeding across. We can rest a level on here and make sure we've got it approximately straight all the way across. And we just kind of rub it back and forth. Then once we do that, we'll take the anchor bolt and we're going to rotate it once it's in to face this way. That allows the aggregate to pile up on top of here so this can't pull out. So we're going to dig it in, and then I'm rotating my hand as I'm doing that to get the anchor bolt facing inwards, the bottom of the L. And again, we'll keep that at about 1 inch height. We'll come back with a string laid along to make sure this anchor bolt is in line with all the other anchor bolts. Okay, let's line it up again. You note the step down here where this is where a door goes, and it's 2 inches lower than the rest of the foundation. The rest of the foundation is 2 inches higher because the straw bales are going on it, and code requires that it be raised up a couple of inches. So it dips down where the door is, so our door pad right here is at the same level as the rest of the house floor. One thing that we did that was a good idea was to leave this one foundation fill for last in case we ran out of concrete at the end. And we did come up a little bit short, so this was perfect because if we have any left over, we can manually fill this in. Otherwise, it was left empty to fill in at a later date. And since it was its own little self-standing unit, that wouldn't have been very hard to do.
We will let the concrete set with the plastic for at least 5 days. The slower the concrete cures, the stronger it becomes, so there's no rush here in drying it out. Several days later, the forms are stripped away, revealing the finished foundation. Now we can start to prepare to pour the floor.
The floor for the entire house will be exposed concrete that has been stained to a stone-like patina. This will eliminate the need for carpet and will also make for good solar energy collection. Not only is this floor easy to maintain, it is so durable it will never wear out. In addition, the concrete will make a good conductor of heat for the backup hydronic radiant floor heater.
What we're starting to do today is to lay down a vapor barrier beneath the floor area. That's going to be followed by 1 inch of foam that will act as an insulation barrier for the radiant floor heat. Up on top of that, we are going to put down a couple of inches of sand. And the sand is just to keep the foam from blowing around. It's been windy for the past couple of days, so that has really helped. The remesh is rolled out on top of the sand, and the radiant floor tubing will then be attached to the remesh. The water for the radiant floor system is heated with natural gas and is used as a backup to the passive solar heat. The entire floor area would then be filled with 4 inches of concrete, and this surface will act as the finished floor.
I think it's worth cutting. We'll just keep this.
This is the coil of the radiant floor tubing, and it comes in one continuous loop that's about 660 feet long. The radiant tubing just loops up on top of the remesh, and at every couple of feet or so, we've attached it with a couple of twists of rebar ties, which is just a piece of wire here. This radiant floor tubing is made out of PEX, and it's been used in Europe for quite a long time. And the nice thing about radiant floor tubing is that it puts the heat where you want it, at your feet, and it heats up the lower portion of your living area the fastest. If you use forced air heat, the heat tends to come out of the forced air vents and immediately go up to the ceiling. This is more like heat from rock and sunlight. It gets warm and it slowly radiates up. There's no dust blowing around, no movement of air. Radiant floor tubing is probably the most expensive heating system to install initially, but it's one of the most inexpensive to run once it's installed, since it's so efficient. And one advantage of using the radiant system in this area is that the local supplier of radiant tubing figured out all the heat loads for us, told us how many loops to put in and how many zones to divide the structure into, which saved us a lot of work. Basically, I took the floor plans to them and they figured out everything, gave us the supplies, and here we are today laying it out. Now that all the radiant floor tubing is in place, it's time to hook it up to the header. And the header is a piece of copper pipe that on this end connects the plastic tubing to a copper pipe, which then goes to our boiler, or in this case, a hot water heater. This upper header here with the orange tube coming out is the hot water in. This is the pipe that will connect actually to the hot water heater. The water will flow in this direction, go through the whole rear portion of the structure, and this is the cold return. The water comes up here, it's lost a lot of its heat while giving it up inside the floor. This copper pipe then takes it back to the hot water heater, it's reheated, and it returns through this pipe.
We're now pouring the concrete floors, and we're going to do it a bit differently than is usually done. The fast and efficient route would be to bring in a cement mixer truck and pour one continuous slab. However, the artist side of me wants to get in there and have additional time to manipulate the concrete into more organic patterns. Therefore, we're going to pour the floor in small sections so that we have time to make artistic decisions before the concrete sets.
Now, another reason for going with this kind of different freeform pattern is because a straw bale house inherently doesn't really have any straight lines. Straw bales are soft. It'd be very hard to get a perfectly smooth surface on it. We're using adobe. Everything kind of has a little bit of a handmade feel. We'll be using mud plastering later on. So to tie the floor in, if we had used a very rigid, very slick surface with square stress mark lines in them, it might not quite have flowed in as well as doing something that's much more freeform like this. So we have curves. Everything in this is kind of curving. Even the floor is not perfectly straight. You've got to kind of subtly pick up a feeling of just, again, the handmade feel of the whole structure.
We mixed the concrete for the entire floor in a rented cement mixer. I had to have an idea of my floor pattern so that we could pour it in irregular sections. This was really a labor-intensive project, and that we were always racing the clock to finish a section before the concrete set up. We screed the concrete, followed up by working it with a wooden trowel, and then finishing up with a pool trowel.
One technique I used for kind of sketching out these lines in the floor was to take a bamboo stick, and just by standing up here, just looking down and sketching in. And from being a few feet away from it because of the length of the pole, it was really easy to see what my patterns were doing. And now I'm just going in and finding those light lines I scratched in with a stick and just etching them in even further. And what I'm using is an edging tool here. And I'm basically just going in and pressing it right into the wet concrete. And you kind of have to dig it in to cut through the aggregate. Like that. And like I said, we're leaving this kind of rough. So I'm then just going over it with a pool trowel and letting it crack and kind of do what it wants. And it's going to be a little uneven, but that's going to be part of the look on this particular floor. Come in with a triangular trowel. So you just keep on going back and forth on this till the cracks kind of look the way you want. You've got the pattern the way you want it. And as it sets up, you can just slowly keep on going back and working into the seams. That's about it. Notice here that I'm using a panel, a plywood panel, so I can get into the wet concrete without my knees sinking in. So I just am leaning on this, and this is distributing my weight over the wet concrete. And it will leave a little bit of a dent when you're through. And that can be cleaned up with the trowel.
Pouring this floor has made for an exhausting few days. However, our hard work has paid off. We've ended up with a floor that's a little bit unusual from the standard concrete floor, and this will look really nice when we finish it up with acid staining and grout a little further down in the project. Finally, from this day forward, the house will start to grow in a vertical direction.
Water systems were also designed for maximum efficiency, without any loss of comfort or convenience for the homeowner. Since 3% of all electrical power in the United States is used to run sewage treatment plants, lack of water efficiency in our homes can mean more pollution and electrical usage hundreds of miles away. Clean water is becoming a limited commodity in our world. Rainwater runoff is usually treated as another waste product, which is carried away by the sewer system, eventually creating more pollution somewhere else. To increase efficiency, this home will use rainwater collected from the roof for flushing the toilet, the cold water line on the washing machine, and for a hose bib in the garden. Hot water and drinking water are obtained from a well on the property. For every inch of rain that falls on 1,000 square feet of roof area, about 600 gallons of water will be collected. Even in the New Mexico desert, with only 8 inches of annual rainfall, there is still enough precipitation to fill a 1,500-gallon tank several times over and store the water for a sunny day.
To find the most cost-effective tank, I did a lot of research as to what was available. Concrete, fiberglass, and steel are just some of the available materials. For my requirements, it turned out that a 1,500-gallon polypropylene septic tank was perfect. They're easy to obtain, they're lightweight, and they cost about 50 cents per gallon of capacity. In addition, the plastic is very easy to drill, and that makes it easy for adding plumbing. A backhoe was hired to dig a hole, and once dug, 2 people could maneuver the cistern into place, thanks to its light weight. By burying the tank, it's protected from freezing in the winter, and the polypropylene will not be damaged by sunlight in the summer. Once the cistern was in the hole, it was just a matter of hooking up the plumbing. The cistern itself is composed of 5 major components. A 4-inch diameter plastic pipe transports the water from all of the downspouts to the cistern. When the tank is filled to capacity, an overflow pipe drains the excess water to a lower part of the yard. A pump line picks up water from the bottom of the tank and carries it to the appropriate water fixtures in the house via a separate plumbing system. The pump and pressure tank are contained within a buried 55-gallon polypropylene drum. 18-inch risers extend the access hatches to ground level. Al is constructing 3 triangular cross braces that will be used to reinforce the cistern walls. Polypropylene tanks are not engineered to go dry. Since a cistern may drain down to near empty between storms, a situation could occur where the tank sides could bow inward from the force of the dirt around it. The braces, which are made out of plastic sewer pipe, should give adequate support with the type of soil that's found on this property. Putting in a little extra work up front to prevent problems down the road is always time well invested. The first few gallons of water coming off the roof is what is most heavily contaminated. It has dirt in it, bird droppings, leaves, whatever. So the first few gallons you want to throw away so only the cleanest water goes into the cistern itself. This is accomplished by using what is called a roof washer. And in this case, we're using a buried small tank that takes the first few gallons of water off the roof and eliminates that from the cistern itself. The water slowly fills up this tank, backs up the pipe, and only then does it start to flow into the simple sand filter. It is deposited into the filter through a perforated pipe just to distribute heavy loads of water during a downpour. Then it filters and trickles through the sand, is collected by another pipe at the bottom of this small tank, and then is taken to the cistern. A drain line is connected to the roof washer so that the contaminated water in the roof washer can be drained off. You just open up the spigot a little bit and it slowly seeps out, and then resets itself for the next storm. When burying an empty tank, there's the risk of distorting and damaging the cistern due to pressure of dirt on the outside. To balance this pressure from the inside, a water truck is used to fill the tank with water at the same rate that the dirt is being added to the outside. The added bonus is that there's now a full tank of water on the property that we can use during construction. This will be a big help since the well for drinking water will not be drilled until much later in the project. And at this point, the metal roof has not been installed on the home, so therefore there's no way to really collect an adequate amount of water.
When the house is finished and the landscaping is in place, the cistern cannot be seen, since it is completely buried underground. Only the access hatch is visible. With the lid removed, the cistern's water level can be checked, general maintenance can be performed, and the tank can be cleaned every few years if needed. Because of the relatively low underground temperature, the water stays cool and fresh. The 55-gallon drum that contains the pressure tank and pump is also out of sight. A flagstone lid allows access when needed. The entire assembly, both the pressure tank and the pump, can be easily lifted out of the drum for maintenance. Flexible hose connections also allow for easy removal of the unit. A small 24-volt DC pump supplies water to the home through a separate plumbing system, putting out enough pressure to accommodate one fixture at a time. The blue pressure tank stores water at about 40 psi so that the pump does not turn on every time a fixture is used. Pumping drinkable water through a municipal water system or even from a well requires a vast amount of electricity, which is particularly wasteful when one takes into account that most of this water will be used for non-potable purposes and ultimately end up in the sewer. Saving drinkable water for its intended purpose makes much more sense than using it to flush a toilet.
Adobe is one of the oldest building materials around. It is an unfired brick made out of pure mud. With proper care, structures made out of adobe can last for hundreds of years. It looks great, it contains low embodied energy, it aids in stabilizing the temperature of building, and it's easy for the novice builder to use. Of all the materials that I used in this house, I think adobe was probably my favorite. It's easy to work with, it's a very simple type of material. You use mud as a mortar, which is easy on your hands, and it just works out really well and gives you a very beautiful, very energy efficient structure.
Now the first course is fully stabilized, which is required by code, and that means that the fully stabilized adobe will not dissolve in water if any were to leak into the structure. Since it is fully stabilized, we've set it in a cement mortar for the same reasons. It will not dissolve in water. Every course of adobe and layer of mud mortar after that is semi-stabilized adobe with unstabilized mud mortar. And that goes up all the way to the top course, and that's capped by the bond beam.
The bond beam is a solid concrete beam that sits on top of the adobe wall and structurally holds it all together. The bond beam also makes for a secure way to fasten the roof to the walls. Adobe bricks are approximately 4 by 10 by 14 inches in size. The main thermal mass wall will be an interior wall that is 2 feet thick, comprised of 2 rows of overlapping bricks. We have the first row running the long ways, it goes with the length of the wall. And we have the other adobes running the other way. This makes up the 2-foot width that we need for the mass storage wall. Now the next course of adobes will just overlap this. We'll have this course running up on top of the seam here. And this gives us a 4-inch overlap, which is required by code. And as you can see, the gap between each adobe is about 1 finger in width. And we'll fill this first course with cement mortar. Every course from now on will be put on with mud mortar instead of cement mortar. The mortar used for the adobe wall is made out of mud itself, just like the adobe block. It was purchased as a dry mix, in other words, just the raw earth material that the adobes were made out of at the adobe yard. It was delivered by a dump truck, and then all you do is you add water to it. And as you can see, you keep it a very thick mix. This is so that as you stack the adobes up, the mud does not ooze out the side. Once it's mixed, you then put it on the adobe block itself using either trowel, your bare hands, whatever. You just get it on to the approximate thickness and then gently place the adobe brick up on top and you wiggle it into position. Notice the strings that we're aligning the adobe blocks up to. This is called a speed lead, and this is a method of keeping our walls true without having to worry about them starting to lean inwards or outwards as we're building them. It's just one of these extra techniques that with a little bit of extra time and foresight will save us a lot of time during the construction process. This is called a story pole. And on this pole we have numbers, each representing the height of 1 layer of adobe. This is how it works. After each layer of adobe is laid, the speed lead, which is sometimes called a mason's line, is raised 1 increment. The line is tightly stretched between the 2 story poles, so it is perfectly horizontal, assuming that we keep the story poles true during the construction process. The adobes are positioned so they barely touch the string. The walls will then be straight and true with a minimum of work.
This is one way to cut in adobe, and what you would do is, with your adobe in place as to where you want it, mark it with your trowel with just a scratch or something to show your cut line. And then what we can do is just, either using the side of a trowel or a hatchet in this case, we just go in and put a score line right where we want our break. It only needs to go down, a quarter of an inch, half an inch or so. We just get a little bit of a ridge there. Then we take the adobe and we have it resting on a cement block, and we just kind of drop it lightly right on the corner. And we get a nice clean break.
Steel ladders placed on top of the adobe every 4 courses. This wire reinforcement gives the adobe additional strength, particularly in seismic areas. Mud mortar is then placed on top of the steel ladder.
The electrical wiring for adobe walls is run right in between the courses of adobe and mud mortar. And as you can see here, the wire's just been laid out on this top course of adobe. And this actually gets sandwiched in between additional mud and adobe bricks.
This is called UF cable. It stands for underground feeder, and that's meant for burial in the earth, which is what's happening here when we place mud on it. These cables lay out on the course in which you want your plugs to occur, and then they come out into the outlet. One difference with the outlet in an adobe wall is there isn't a wooden stud to nail it into. So what I've done here is taken a 3/4 inch by 3 to 4 inch width of scrap wood and screwed the electrical box directly into the piece of wood. And we've used what are called strain reliefs on the back. The wire will not pull out. And we just leave it in this state until the electrician comes in and wires it up later on.
This then gets adobes laid up on top of it, again with mud mortar, and it actually forms a sandwich and really locks this into place so it can't move.
Sometimes it's necessary to attach another wall, such as a frame wall, to the adobe wall, and there are a couple of different ways of doing this. You can use a gringo block or what are called stab bolts. A gringo block is made out of 2x4s, and it's just a hollow block that is inserted in place of an adobe and then filled with mud. This then gives something to nail into, unlike the adobe block, which does not have any structural strength for taking in nails or bolts.
Now this is a bolt that we've embedded in between 2 courses of adobe, but we've used regular cement mortar. The stab bolt actually has a slight S pattern to it, so when this is set into mortar, this isn't going to go anywhere and it's going to be rock solid for our structure.
Adobe is just such a great and fun material to work with. Every day, your wall goes up in a completed form at every step. Unlike a frame wall where you need to add sheetrock and taping and plaster and things, an adobe wall is finished at each step, so it's really a beautiful material to watch go up.
Thermal mass walls cost more initially than conventional wood frame walls. This expense is offset, however, by the fact that all air conditioning costs will be eliminated, including ductwork and installation at the time of construction, and maintenance and electrical costs over the life of the building. Looking at the entire package allows a better assessment of long-term value.
What you're going to see here are 3 different types of forming up the bond beam forms. So what Tom is doing here is he's cutting adobe blocks with a power saw with a masonry blade on it, and we're using these as the form itself for the bond beam. The first system we're using here is for the 2-foot thick solar mass wall. And since it is 2 feet thick, code in New Mexico says that the bond beam only has to cover 2/3 of the width. That gives us a little bit of playroom to use a different material for actually forming up the form for the bond beam. So I'm just putting these into place with mud mortar. They're cut to the right height, so we're at least 6 inches thick. And we're forming a trough that we'll then be able to pour concrete into at a later point. Now on narrower walls, like this standard 10-inch thick adobe wall, we're going to use a more conventional approach to forming up a bond beam, and that is with lumber. So here we're using some scrap lumber, and Al is affixing this kind of pre-assembled piece into position that uses just kind of a friction fit to keep it from falling off. There are wire ties on the bottom that crisscross, and that makes for a rest for the forms to sit on. Again, the accuracy here is very important. You want to make sure everything is straight and level. You want to make sure that the pour will be at least 6 inches thick. And once everything is in place, you can go back and start adding your number 4 rebar. And notice that as it comes out of the 10-inch wall into the 2-foot thick wall, it actually crosses over to the far side. This is a technique that makes for a very strong wall. The 2-foot thick section of bond beam has 3 parallel rows of number 4 rebar. And it's sitting on little steel chairs, so this gets the metal kind of suspended within the concrete itself for additional strength. Since this is a small house, using buckets to carry the concrete up to the top of the wall was no big deal. By inserting anchor bolts into this bond beam, roof trusses can then be bolted onto the adobe wall itself. Something else we have here is bond beam block. And it kind of looks like a cement block, except it has these slots cut in it. With these slots, we can actually knock out the side. Now this little 3-inch piece here then becomes the support for our rebar, which is really handy. And we then take the block, mortar it in place, level it up with our speed lead. We lay our rebar in it, and then this whole cavity gets poured with concrete.
The thermal mass walls are finished. The project will now move on to wood frame construction. In this particular house, the load of the roof sits upon a post and beam structure. The straw bales will be used for infill only and do not take any structural load.
What this means is that we have a series of 4x4-inch posts that are supporting a beam on top. In this case, this beam is about 4 by 8 inches. It's actually made out of two 2x8 pieces of lumber that are nailed together. So the post is carrying the load, as I said. It's coming down to this assembly here, and here's our foundation for the straw bales. Again, it's about 18 inches wide. It's raised 2 inches off the floor to prevent any moisture from getting into it. And we have the rebar that we put in during our foundation pour. Now the straw bales, again, they're strictly for insulation and for actually forming the surface of the walls. They're not carrying any load. And this is how it needs to work right now for code in this state anyway.
The remaining walls within the house are all standard wood stud construction. We're using 2x6s because all of the drain, waste, and vent piping, in addition to the freshwater piping, will be run within these walls. There are very few frame walls within the house, and the ones that do exist are all used for plumbing. By using a 2x6, we are able to drill a 2-inch hole for the drain, waste, and vent pipes right through the stud, and it stays structurally strong. We now come back and install the connector plates to the J-bolts that were installed during the foundation pour. These plates bolt into the J-bolts, and this will allow us to securely mount the 4x4 posts of the post and beam structure. This metal cap will keep the wooden posts from contacting the concrete and absorbing moisture.
We will set this corner post and plumb it in both directions, embrace it, and then we can set a line in order to set the remaining posts.
Each post is then nailed into the connector plate, and we will use a level to make sure it's plumb. Temporary cross bracing is then added to 2 sides. This is very important for keeping the post plumb during the construction process. Once the roof trusses are in place, these temporary braces will be removed.
Right on.
Right there?
Right there.
Okay.
You can hold it.
All good?
Yep.
We will then use our water level again to ensure that the beam will be at the same height everywhere in the home.
Not quite. We're off by about 3/16.
We pick one post to be our reference height, and the other end of the water level is then moved from post to post, and that exact same height is marked on all of them. It is then just a matter of cutting off the post at the marked height. It's accurate and it's simple. The actual perimeter beam itself is made out of 2 2x8s nailed together, making sure that the joints are staggered. This continuous beam runs the full length of the house and is extremely strong. Due to its length, it will take several people to lift it into position.
Get forward, and then once you get past the second post, go back, and then we'll come forward again.
I got it.
Okay, ready? Dropping it. Perfect.
This particular frame wall was built on the ground and then tilted into position. We position it on the J-bolts, get it leveled, add some shims to hold it into place, and then secure it. Al is installing a 2x6 sill plate to the top of the adobe wall bond beam. This sill plate is used for attaching the roof trusses to the adobe wall. The wooden plate will be bolted into place with the bolts that were set into the bond beam when it was poured. Two-by-six ceiling joists are used in both the entry hall and the kitchen. These joists will be a visual element of the ceiling and also support the floor and the loft. On the south wall, the connection to the beam will be hidden within the straw bale wall. Metal brackets were used on this side for maximum strength. The joist connection on the opposite wall will show, so on this side the joist was nailed in from the other side. Again, it's still a very strong connection. The loft floor is made out of aspen wood. Aspen is fast growing and is considered more environmentally sound than pine or oak. The downside is that it's very soft. Since this is not a high traffic area, the floor will not receive a lot of wear and tear, so the softness will not be a real problem. Again, this adds to the environmental quality of the house. We are using a wood that is appropriate for the location.
Our roof structure here is made out of what's called a pre-engineered truss. These were assembled off-site by a company that specializes in this type of system. And you can see it's just made out of 2x4s. This saves on wood, it's extremely strong, it saved us time and some money in having not to have to build these ourselves.
The specifications are sent to the truss manufacturer, and they do all the engineering and assembly. On a specified date, the trusses are delivered and are ready to drop in place. The depth of the truss was sized to accommodate at least R55 insulation. In a small house, the trusses are easy to maneuver and can be carried by two people.
Oh, this is great. Yeah.
Tom and Mark are installing a 2x4 vertical support that will be used to secure the first truss. This is a temporary brace and will be removed when all the trusses are in position. A rope is attached at the top of the truss, and you'll see why we're doing this a little bit later on.
That off this way, or you got off that way. Doesn't matter to me.
Yeah, why don't you take a bunch back and I'll just tie this end off.
Yeah.
One by one, each truss is positioned and secured. We indicated the position of each truss ahead of time with a pencil line.
I just want to make sure it's perpendicular when you nail it off.
We used metal straps wherever a truss was to be connected to the beam. These are also known as hurricane straps. They make for a very strong mechanical connection that is superior to just using nails and screws. With these straps, the roof will not pull off in a severe wind. As the day progresses, the trusses continue to be dropped into position at an easy pace. This is a temporary cross brace that will hold the trusses in alignment until the roof sheeting is installed. In the short term, they will keep the roof from racking back and forth. Later on, this temporary cross bracing will be removed. Now we'll get back to the rope.
How's that? It can go out a little bit.
As Mark pulls on the rope, the truss can be made perfectly plumb with the beam below. Tom is using a plumb bob to visually see where the truss is in relation to the beam.
You can do it.
So when the plumb bob is right over the beam, we know the truss is also right over the beam. The pre-assembled trusses do not include the roof overhang for the control of solar gain. So what we're going to do is attach a 2x6 rafter tail directly to the truss. This saved a considerable amount of wood since the upper member of the truss can be constructed out of 2x4s instead of 2x6s. This short 2x6 is easily attached to the truss and will be cut to the proper length when all the pieces are in place. The 2x6 was used mainly for aesthetic reasons. It just looked better than a 2x4, and we were able to obtain the look without overbuilding the entire pre-assembled truss. The next morning, with just one day's worth of work of installing roof trusses, we can start to walk through the rooms and get a sense of scale for the first time. This is really an exciting time. I mean, finally, at last, it's starting to look like a house. A lot of the work to this point seems somewhat invisible. Now, while driving up the street, I can actually see my pencil sketches taking shape into an actual building. The roof over the north rooms of the house will be built by us instead of using a pre-built truss. Tom has cut each upper 2x6 to the proper length, and he is now notching it so that it comes in direct contact with the 4x8 inch perimeter beam. This gives the 2x6 a flat surface in which to nail and screw it to the beam it is sitting on. Mark then screws and nails the other end to the pre-manufactured trusses, and this forms the lower pitched roof on the north side of the house. This section of roof is over the bathroom, so two different directions of the roof will meet together. This is a very low-tech tool that we built. Since these rafters will be visible under the roof overhang, we wanted to ensure that they were at 90-degree angles to the beam. So we built this giant fork that is used as a lever to twist the rafter to the proper angle. Al then installs a metal bracket that will permanently hold it into position. These metal brackets add tremendous strength to the roof and will prevent it from blowing off even in extremely strong windstorms. Again, for a few more dollars in materials and a few extra minutes of time, it's cheap insurance.
Three different elements make up the final roof assembly. First, a layer of OSB, which stands for Oriented Strand Board, is screwed into the trusses. This is followed by a layer of roofing felt, which is also known as tar paper. The final layer is corrugated galvanized metal sheeting. Note that the oriented strand board does not continue into the roof overhang. 1x4 lumber was used instead. This was done purely for aesthetic reasons. The wooden slats, with the exposed metal roofing in between, created a much nicer effect than solid OSB sheeting.
As the roof sheeting is installed, the temporary cross braces are first removed. The oriented strand board comes in 4x8 foot sheets. This nail is being used strictly as a spacer. The width of one nail allows the sheeting to expand and contract with the temperature and humidity, so we leave this slight little gap in between to prevent buckling down the road as the temperature changes. Each sheet is then tack nailed into position, and then this is followed by using screws to make a very strong connection to the trusses. This is called an H-clip, and it's a simple metal bracket that is slipped onto the edge of one sheet. The next sheet of OSB then slips into the other end. It keeps the sheeting anchored together between the trusses and prevents warping.
Those work well.
To fit various schedules of the work crew, it is decided that the straw bale workshop will be held in 7 days, on a 4th of July weekend. The metal roof sheeting will be installed after the workshop, in case any wood sheeting needs to be removed from the roof during the installation of straw bales. In 1 week, this project will take a dramatic visual turn away from conventional home construction.
Hi, I'm Stefan Bell. I'm a straw bale house builder and I coordinate straw bale workshops. And this weekend we're having about 15-20 people to participate in this communal effort of building straw bale walls. These people participating will be doing a lot of labor, they will learn a lot of knowledge, and during that process it will encourage them to build their own homes, therefore spreading the word of straw bale wall building. A lot of people call straw hay, and it's basically straw is a dead material. After they harvest a crop, which can be wheat, rice, oats, barley, there's the stalk left over. They normally burn the stalk and produce more carbon monoxide on the planet. What they do now is they reharvest it, they cut it, they bale it specifically for a certain compression factor, and we get these beautiful large blocks called straw bale blocks. So it's a recyclable material, and we're creating a new industry for the farmers and the people that supply this. And you'll notice too, this is what we call a two-stringer bale. It's a polypropylene string. These things are about 35 pounds each, they're 3 feet long. That's a standard size. They do come in 2 different heights, either 14-inch or 16-inch. Specify that you want the 16-inch because that makes 7 courses. If you get the 14-inch, you have to add another course, which increases your cost again and your labor. It's $1.50 a bale, and then $500–600 for delivery, which makes it $2.50 a bale. We have the 15-pound felt paper on top of the footing to prevent moisture from wicking upwards. What we do too is with the straw, when we stack it, it's alternating in courses like bricklaying, so it's stronger. In Ted's situation, he's got some corners actually over there where there's just like an 18-inch length, so we have to custom make 18-inch bales, 7 courses high, and we just stack them. It's a short distance. He has a system here, what's called the straw bale is what we call infill. It's inside the post area. But we have to notch a lot of bales to wrap around the post. That's more work. The fastest way to do your bales is to do your post system inside like the old Mennonites did, and then have the straw just go continuous. That makes it a lot easier as far as stacking straw. But there's more complications and engineering involved in that. Quick point, the rebars that are sticking up, they're minimum 7 inches into the footing, and they come up 1.5 courses normally. If you're at least 1 course up, you're fine. That will do right there. Now see, we can see with the string line too, this is pretty nice. So this we can either kick over or use a sledgehammer. Yeah, let me see, 3 feet. So what we're going to look for actually is a 38-incher because they'll butt up there. And this looks like could be close to a 38, so we'll use this one. The trick on this one is we're going to line it up so it's tight against the other bale end. Okay, right there. Good. Okay, now we'll slide it down again. Good. All right. And this one we have a little proud, so I'll just kick it in a bit so the string is a little loose. Now you could kick that and bring this out a bit, and I'll hold that. All right, so that's just doing fast tweak adjustment. Now the other thing we do too is, watch your head up above, stand on it, stomp it down so it sits real nice. The string here is at a 14.5-inch height. What that does for us is when we put the bales, we'll be able to have a straight line. The little things that take a few minutes to put up will help the job. So it's better to do this, and we get a very straight wall, and at the end when you stucco or plaster, you'll get a natural, organic waviness to it anyway. Okay, so you guys organize this next one, get a bale and figure out where the notch is. Put the bales with the knots up, because the bales are curved. It's a lot easier to compress it with the curve being in the center, or what we call a crown. So I'm going to sight the notch out. And then I'm going to get a short piece of string here, because I want them to miss this. Just going to tie this quick. Pull it through here, through here. I'll do the same on the other side, and then I'll give it to somebody to notch. Full bale, full bale, full bale, okay. Can everybody come over here and we'll show you something else about what has to be done at every course. And this is what the code people want. So what they want is a minimum 6 inches up the post and 6 inches in to the bale of metal lath. And that's to tie it to the post and beam system. So you can do 4 nails or put them sometimes 6 depending what they want. So then what you do is you take the landscape staple, which you can get at the nursery. This is a 6-inch one, you can get a 9-inch one. And then you take that, and what you do is you put it through the lath and you're on an angle and nail it in. And do it both ways, and that holds the straw in to the post. Oh, a nice 38 would fit in tight. So we need to look for a 38-inch bale. Who wants to do that? These are 5-foot rebars, number 4, 1/2 inch. We are at a 4-course height, which means a 5-foot rebar is the length, the height of 4 courses. From this point on, we put 2 rebars per bale, and they're 9 inches in from the end. That's the code. Every course after this same 2 rebars go in. In the end, what happens is on the next course, the bottom of the rebar hits the top of the first course. Next course up hits this course. Next course, this course. So what you do is when you pound them in each course after that, you make the head just slightly visible on top to know you have rebars in there. And that is to tie it in all together. In the end, when you finish the whole wall, each bale will have 2 groups of 3 rebars grouped together. When he is done with the top course, code-wise and sensible-wise, you take 4 mil or 15-pound felt paper all the way across the top of the course, 6 inches down both sides, pin it from the sides, and that's a moisture barrier. Protects it in case you ever have a leak from the roof. It will run off the sides. So at least that way you're safe. So that one's gonna slide right in here. Now we have a nice overlap there. This is looking real good overall. He'll be able to tweak. You know, I can look down here and see the odd bumps in that. Considering the workshop and what everybody is doing, this is superb. Because, you know, to get it this clean, nice and square and everything else is wonderful. And Ted can come out here tonight at midnight and tweak it all for us. And this one here. Okay. It's got some windowsill members here where windows go in, and some windows are what we call floaters. It's just a box, goes on top of the course of straw, and then the straw goes on the sides. Then you say, how do you stabilize that? You drill holes in the wood, you take the 1/2-inch rebar, you drive it through the hole into the straw, and that locks it in. And anyway, we're coming over to this side here. It's a long stretch of straw bale wall with 4 windows, very nicely placed. We have the roof overhang, usually 2 feet for protection of the walls, especially since they're done with mud. It still needs to be completed, but it's going to have a beautiful effect in the end when it's done. Very simple. And then coming into this corner here, again, we have the gable end with the window up above, a loft inside. It's almost completed up there, the overhang again. So a real nice, very simple house. In the end, cosmetically, it's just going to be a beautiful sight to behold. The straw is nice because it's homeowner oriented, because it's very easy to learn how to build with straw. You still need somebody, if you don't have the skills, to figure out all the carpentry, posts and beams. But this is the fun part. You can do workshops with this.
By the end of the 2-day workshop, over 80% of the straw bales are in place. However, there is still some additional work to be done before the bales can be mud plastered. An electric chainsaw can be used to bullnose corners around the windows and also to level out the sides of the straw bale walls where needed.
Wooden shelves are constructed above the windows and doors. These are made out of 2x4s and wafer board, and they will support the straw bales above all window and door openings. Loose sections of straw bale will fill the void of the shelf itself. Then, bales will be cut to fit between the roof joists. This phase took quite a bit of work to fill in all of the voids, and it was a little bit tedious. Stucco netting is nailed to the exterior framing, and more straw is stuffed behind it to make for a nicely contoured base for the mud plaster. Much of this work was done strictly for aesthetic reasons. It also made for easier mudding, since most of the irregularities of the walls were filled in with straw. Loose straw will be stuffed behind the stucco netting on the gable ends. This will even out the walls in preparation for the mud. With most of the straw bale work accomplished, the roof can now be completed and made waterproof. Roof felt adds an extra layer of water protection. Any water that were to leak through a screw hole from the metal roof would flow safely away. The material is stapled to the OSB base. As we place the first sheet of the metal roof, we find out that there is a problem. The east side gable end of the roof is not perfectly parallel to the west side. Therefore, we're going to have to make a slight diagonal cut on the metal sheeting on the east side so that it will align to and be parallel with the west side.
This is kind of an example of an error early on that has compounded throughout the process. We had 2 walls meet not quite at a right angle. So what happened was it threw off our framing below, which in turn threw off our beam, which in turn threw off our truss, which in turn threw off this. As you can see, we've had to cut this particular panel at an angle in order to kind of straighten our leading edge. We ended up having to trim about just over 2 inches on this cut to straighten this out.
And then the roof will be straight all the way across.
Right. This leading edge will then put us true and we should line up just fine with the other gable. The first piece is critical because all the other pieces follow. So it's very important to get the first piece to lay properly, and then the other ones just slip into place.
I think what's interesting is that because it's built out of straw and adobe, it's kind of a loose house, but when you get to something like a rigid roof that's done in a grid, it has to be very tight.
With this type of roofing system, especially, I mean, I think if we were going with, 3-tab shingles or shake or something, I don't think it would have been a big deal.
Sheet metal is very easy to work with, and simple cuts can be done with shears. Larger, broader cuts can be done with a powered handsaw that uses a metal cutting blade. In this case, we've made a cutout for the skylight. A metal roof was chosen for a couple of reasons. They are very durable, and equally important, it will not contaminate rainwater that is collected for the cistern. Asphalt-based roofs will contaminate roof water runoff. The final step is adding the ridge cap, and our roof is complete.
The roof on this house does more than just keep the rain out and the heat in. It's also used for collecting solar energy. And you can see on the panels on this roof, those are photovoltaic panels which convert sunlight into electricity. 100% of the electrical needs for this house are met by those panels. That runs everything, all the appliances in the house, all standard AC equipment. That includes the refrigerator, computer, television, everything. The really neat thing about these panels is that they're 100% pollution-free, there are no moving parts, and they'll run for decades.
Since the workshop was built before the home itself, the entire photovoltaic electrical system was initially installed in the workshop. This supplied electricity for the entire building process, powering all the electrical tools that were used, including chop saws, cement mixers, and drills. The black box is the DC side of the system, which draws power off the roof panels and charges the battery bank. The electrical storage unit consists of 12 L16 lead-acid batteries. They are contained within a box that is vented to the outside of the building in order to let the hydrogen gas that the batteries generate while charging escape. This battery bank is sized to provide approximately 3 to 4 days of power without any sunlight, which is more than enough backup for this part of the country. The white box is called an inverter. It converts the 24-volt DC power from the batteries to 120-volt AC. With the roof in place, the photovoltaic panels are moved from the workshop roof to the roof of the main structure. The inverter and DC charge controller will also be moved to their permanent location in the home. The house is now ready for electrical wiring.
My name's Joe Yarkin, and I have a small solar electric contracting company, and we're going to rough in the wiring to this house. It's a standalone photovoltaic system and would be doing the rest of the solar electric system, but I'm going to be off to Antarctica for about 5 months and won't have time to do that. In Antarctica, I'm doing solar electric wiring down there for the National Science Foundation for science projects. Antarctica is one of the most remote areas on the planet, and solar energy is very good for summertime operations down there. One, because they get 24 hours of sunlight, and second, because it's reliable power with no moving parts, and that makes the economics of solar energy very favorable. Okay, the first step in designing an electrical system is making an electrical plan that the owner can express his desires about where he or she would like switches, plugs, and then combine them with the National Electric Code's requirements. After I got that plan, allowed me to make an estimate of how much time and energy it was going to take to do this. I divided that plan up into different circuits. And when we're wiring a straw bale house, the first sequence is looking at the plan and planning out each circuit, and then finding out where the wire or the conductors are going to touch the straw bale. And in those places, we take a chainsaw or a knife, and make sure that there is a raceway that we can shove the wire into the straw, where it's less likely to be hit by any kind of nails or anything like that. That coat, of course, was designed for wood-framed houses, and but we interpret it the same, and it's enforced the same. It needs to be 1.5 inches in. Then take the wire and wedge it into the channel. So I use a kind of a dulled stick sometimes and pound the wire in a little further so it'll stay. We have run what's called UF, or underground feeder cable. This is a moisture resistant and heat resistant, very tough cable with a tough outer jacket. Another part was how the boxes are actually attached. We use metal boxes. They're preferred because they will outlast plastic in attaching the receptacles to them, and they're stronger in that way. They also make a better connection to a stake. What we do is attach a stake to them using a couple screws and pound that into the straw and leave it out about 1.5 inches, because another property of straw bale that I've learned is that it takes a lot of stuccoing and plaster to build out the wall and make it nice and flat. And here we have a light fixture that is attached to a 2x2 about 12 inches long and then pounded into the straw. This is a regular metal box that will be covered up to here in outside plaster or stucco, and then a waterproof gasket and fixture will be attached to that in the final part of the electrical installation from the floor level. And we could match that.
Threading electrical cable through a straw bale wall is done by taping the UF cable to a large metal needle and pushing it through the wall.
And now we have our 2 wires out here that will power this light and then send it on to the next light, which is coming out of the wall right over there. Here we have a triple switch. This is actually 3 different switches. That one is attached to the outside light, another is another outside light that's on a 3-way switch, and the inside hall light. This is simply made by ganging 3 metal boxes together and then attaching that to one of the wood structural pieces. How I run wires from place to place in walls is we look at areas that will be concealed, and we drill holes using a power drill through the wood at least 1.5 inches in from any finished surface to protect it from nails or screws. Then wire is pulled through these wireways and directed towards either the following receptacle or to the service entrance panel, which we call the home run. This kind of cable that we're running here will never be in contact with the straw bale or the adobe. So we used a wire commonly referred to as Romex. It's not suitable for wet locations or areas that may be moist. It is easier to work with, so we used it wherever we can in the stud walls. This box is a side attached, and this is more a standard stick frame wiring technique.
Joe Yarkin is on his way to Antarctica, so another electrician will come to do the final hookup of the photovoltaic system. This home uses only compact fluorescent light bulbs. Compact fluorescents last significantly longer than traditional incandescent bulbs, making them much more cost-efficient in the long run. They also use much less energy and generate much less heat, which helps keep the home cooler in hot weather. Compact fluorescent bulbs are a good economic choice for any home or business, but for a photovoltaic-powered structure, they are mandatory. An honest use of materials means that materials are chosen for their natural properties, not forced to serve some function for which they are not suited. All arches over doors and windows were formed with flexible bamboo rather than rigid lumber cut and pieced together. The bamboo, when curved and tied together with wire, becomes very strong. Partial bales of straw were then used as filler on top of the bamboo. The arch is covered in wire mesh in preparation for mudding. Cob, which is loose straw with enough mud added to make it stick together, was used to blend the arch naturally into the wall. Expanded metal lath is added around all windows and doors. It is affixed to the bales with landscape staples. And all the adobe walls will have wire netting nailed into place as well. This serves as both structural reinforcement and to help the mud plaster adhere to the adobe wall. Passive design measures, such as paying attention to which way the windows face in relation to the sun, will add little or no expense to the construction cost of the building, but will substantially reduce long-term heating and cooling costs.
That looks really good. Let's check it this way. Looks great.
The windows themselves are double-paned, argon gas-filled, and have a low E coating that aids in reflecting heat back inside during the winter months and keeps heat outside during the summer. This part of New Mexico is 5,000 feet above sea level, so the argon gas between the panes will soon leak out due to the low air pressure, and consequently will not contribute to the insulation value of the windows. It is often recommended that low E coating not be used for south-facing windows, in order to let more heat energy into the home in winter. For this house, however, it was decided that keeping the summer heat out was more important than a slight decrease in winter heat gain, since the house has no mechanical air conditioning system. Therefore, low E glass was used on the south-facing windows.
Corrugated cardboard baffles were used to reduce the size of the gap between the outside roof sheeting and the interior ceiling. This saved money in that we only need a 15-inch deep space here for blowing in the insulation to R55. The baffles also prevent the insulation from sliding down the steep pitch of the roof to the lowest part of the roof. With the corrugated cardboard baffles in place, the insulation can be blown in to fill the entire remaining space at a constant depth. Sheetrock was then screwed to the roof trusses. After working with very pliable materials like mud and straw bale, sheetrock was a real letdown. It's a rigid material that requires precise installation. An adobe wall with slight curves and waves looks really beautiful, but a sheetrock wall or ceiling with waves in it just looks like poor craftsmanship. Initially, some sheetrock panels were temporarily left out at the top of the ceiling so that there would be access for blowing in insulation.
Blown-in cellulose will be used to insulate the ceiling. Equipment for blowing in cellulose can be rented from a local home supply center. Cellulose insulation is made from recycled newspapers with a small amount of boric acid added to make it flame and insect resistant. It will be applied to a thickness that will give the roof an R55 rating, even though code in this part of the state only requires insulating to R30. Since it is being blown in dry, the insulation will eventually settle to around R50. One advantage with blown-in insulation is that it fills in all the cracks and gaps that often remain when typical batt insulation is used.
With the insulation in place, the seams of the sheetrock are taped and mudded, and the screw holes are filled. The term mud, when used with sheetrock, refers to a plaster-like substance and not the earthen mud we're using in the rest of the house. Again, this is a procedure that takes some care in order to get invisible joints. 3 coats of sheetrock mud were applied and then lightly sanded. While we work on the inside of the house, the well drilling company arrives and gets to work on drilling the well for drinking water.
All homes in the village of Corrales use individual wells for drinking water and on-site septic systems for sewage treatment, since neither a central sewer system nor water system exists here. It uses a 1,000-watt, 120-volt submersible pump that runs off the AC side of the photovoltaic system.
This is our pump, Fairbanks Morse. This is a half-horsepower single-phase motor. The lower part is the motor assembly, and the upper part here is the pump. We have attached a 1-inch plastic pipe to the pump, as you can see here. We've attached a polypropylene rope to the pump, and we'll be using the rope to lower the pump down into the well once we start that part of the operation. The suction level of the pump will be about 20 feet below the last measured water level. In this case, about 50 feet below ground level, so the suction level of the pump then will be about 20 feet below that. The overall well depth is about 280 feet. It's a fairly heavy unit, weighs 30-some odd pounds. In order to get good control over the dropping of the pump down into the well housing, we've stacked up some straw bales here and put a steel pipe across the top. And what we will do is we'll take the polypropylene rope which is attached to the pump, and we will make a couple of turns around this steel pipe so that we'll have very good control over the descent of the pump down into the well housing. Okay, I think we got it in place. Okay. We're now ready to put the cover plate on. And this will make a weather-tight seal with the electrical junction box. We've assured there's an adequate amount of water in the well. We're going to check the clarity of the water now. It's pretty clear. The pump is drawing about 9 amps, and we're pumping about 11 gallons per minute.
With the mud plaster workshop quickly approaching, there is a final push to complete all the wall detailing. A 2-foot-high band of conventional cement stucco is used for the bottom of the exterior walls. This is an area where mud plaster alone can be damaged by rain splashback or even by watering the garden. The 3-coat cement stucco makes for a durable zone of protection and also adds visual interest to the building.
2 coats will be applied before the mud plaster workshop. The 3rd coat of stucco, which will be a color coat, will be applied before the finish coat of mud plaster. A couple of inches of cement mortar was laid atop the straw bales below our south-facing windows. This will be the base for the flagstone window seats. We used cement mortar when the flagstone would be sat upon or was going to take any significant weight. Otherwise, we just used cob and mud as a base for the stone. The window seats are a free bonus in straw bale construction due to the thickness of the walls. They look great, and they're also functional in that it gives additional places to sit, which is always welcome in a small house.
An important goal in designing this home was to demonstrate how various elements of a building can work together harmoniously, as opposed to being separate components which were simply assembled under one roof. On a sunny day, the roof becomes part of the electrical system, and on a rainy day it collects rainwater for the cistern. And by letting in just the right amount of sunlight, the windows can work in conjunction with the floor and the walls to keep the inside of the house comfortable at any time of the year. Alternative building materials expert Stefan Bell has returned to lead the 2-day mud plastering workshop. The first of 3 coats of mud will be applied to all the straw bale walls during this all-volunteer workshop.
This mound of dirt is actually a premix supplied from an adobe company. It's used for making adobe bricks. It has a lot of aggregate in it, as you can see, but it has sand and clay mixed together. So what we do, what I normally do is I get clay separate, I get sand separate. They're both pure. I use 70% sand, 30% clay, and mix the two together to get the right mud mixture for the wall plaster. In this case, what we have to do is we have to take this particular soil and go over here to a screen the aggregate away from it. The dirt, clay, sand goes through it, and then we have a nice clean heaping mound of it. And what I'm going to do is a little bit of a compression test, and it tends to break apart easier than normal, which tells me there's a higher sand content than a clay, the amount of clay that should be. So my suspicion is that there's probably like 80% sand, 20% clay. Should still be okay. The other way to tell is rolls down real easy, which is a characteristic of sand. But we're okay with it. And then what we do after that is we take that particular clean mix, throw it into cement mixer, and we do basically 12 shovels of it. Then we do 4 large hands of chopped straw, and then put in ½ pound minimum to 3/4 pound of wallpaper wheat paste as a binder. Mix it dry first so each molecule mixes around. This is real nice powdery stuff. Has to be dry mixed. If it's wet mixed, normally you get little balls forming and they end up being pockets on the wall. And then we add the water to it, mix it to a point where it's just soft enough, like a mousse mix, a little bit moist, so it spreads real easy on the wall. And that ends up being the mud plaster mix we use both on the outside and inside walls. So that's that. So let's get rock and rolling. The mud is basically composed of sand, clay, chopped straw. Proper mud mix that does not crack or come off sandy, deteriorate, is basically 70% sand, pure sand, 30% pure clay. And that combination has the stable integrity of not decaying, breaking, or splitting, or coming off the wall.
So that's what we did, is we got 18 shovels of the premix, 3/4 pound, 5/8 around their wheat paste, 4 big hands of straw. We dry mix it for at least a few minutes so every molecule goes around every molecule. Then we add 4 3/4 gallon bucket of water, so it's already pre-calculated. We get this beautiful dead-on mix. Okay, see that's a nice mix. It's wet enough to go on real easy. And on the south wall, the sun will dry it out just right. So this is beautiful. Oh, this is primo. And you want to work it every way possible. Get it in there real tight against the straw. So it takes a lot of forearm, shoulder work to get that in there. Because it isn't as hard as it seems. There's just some tricks to it and some body motion. And one of the main body motions in troweling is don't use just this motion. You want to use the whole body. And you'll see plasters, they're moving like a conductor. And that puts less strain on one part of the body. You can mud plaster direct on the straw or with the wire. And the wire isn't really necessary, but it does make it easier. But you can do a whole building without mesh at all. The only areas around the doors and windows where you want expanded metal lath for the bullnosing and for the connection to the door around. That's a standard feature that you do. And what I find without the wire, you notice it has little grooves, the straw. We usually either chainsaw these flat or just leave it, but here when you put the mud plaster on with the trowel, you have to vibrate your hand to work it in. So it's a lot of work on your forearm wrist. So we use a bit more of a wet mix for the scratch coat for it to grip better. If it's too dry, it's really hard to apply it and for it to stay initially. Once it's on there, you can put more on real easy. Here's a deep pocket. This is an interesting scenario. And most people load up their trowel with a little bit. I'm going to load up a lot because I want to hit that pocket and make sure the mud grabs. So if I didn't load it up that much, it would have fell out. Same here, there's a pocket. Load up a lot of it and then just force it across and you're in there. Flatten it out at an angle, the longest line, and what I do is I slide to get a whole edge. Then I'm holding it this way, then it's a quick turn around. Same thing again. Now, I've got a basic edge here. Then what I do is I take a lot of this stuff, hit it again and come across. Isn't that nice how that works? So you see how that window looks gorgeous? Just at this stage here. And what this does too is by being more meticulous with your scratch brown coat, by forming things very good, is that when you go to do your final coat, it's going to be so easy to do the final coat and make it look incredible instead of trying to save and work all the mistakes you neglected on the first two coats. You can see the color changing. There's lighter spots on there, so those areas the sun is already curing the mud. It dries very fast when the sun hits it. And so what we normally do is keep a check on that. If there's a hollow, then we want to put some more mud on that because it's already firm enough to grab it. Throughout the whole day, we can actually do what's called the scratch coat and a fill-in coat to start flattening out and making it nice and smooth and curvy. That's the advantage of the outside plaster on a sunny day. Today's not a hot summer day because we're in November, so it's in our favor. In the summer, I mean, you'd be going across in a half an hour, all this stuff would be already hard. And then it's harder to put the other mud on. So, here we have an indentation. This mix is a bit thicker because you can see the way, what I call a slump mount, it's holding pretty nice. It's not dripping, so it holds pretty good. Go in there, press real hard, and I'm visually checking it out and I can see certain hole areas, and I also throw it on instead of just placing it, so I smash it. And once I have it on, then after that, I'm just gliding to flatten it out a bit. I'll use the trowel both ways, left and right. You notice how I'm coming across to overlap. So again, there's just a little bit here. The mud mixture too on the outside, you got to be careful. You can't put it on knowing the temperature goes below 32 degrees. You can't have it freeze, it crystallizes. Starting in the morning, you want to do what's called 32 climbing, and you don't want to have it drop below 32 at night. Inside is the advantage where you don't have the sun baking the mud, drying it out fast, is that it'll stay wet for 3 to 7 days, which means you can keep working on it day after day after day. So that's the bonus on the inside, that you can do that continuously, whereas with gypsum plaster, Structuralite, any of those finishes, you've got 20 minutes, 30 minutes, you can't take a coffee break, you know, it's a nightmare story sometimes. So right up. Through that day workshop, 2 days, you share a family situation, give to them all your knowledge unconditionally. And everybody else goes away and say, I learned so much, and now I can apply it to myself, and then give it to others. The mud has so much moisture in it. People forget that, and the moisture rises due to the heat up in the top. If you have drywall, any type of wood decking, you'll actually, the next couple of days, you'll come in and you'll be dripping wet. So you need to open all the doors and windows every day until this mud dries. And at night, have a couple of windows open with a fan and cross ventilate. Normally, the scratch coat implies that when you put the first coat on, you then scratch it so that the second coat grips all those little channels. With stucco, you have to do that. With mud, you don't have to scratch it. You can just leave it like this, smooth, patchy, and then when you put the second coat on, you sprinkle this with a garden hose, put the second coat on, and the two become one again. In the end, you end up having about anywhere to inch and a half, 2 inches of mud on the wall. It varies. You know, this wall actually, if you had seen it yesterday, I mean, it was bad. I mean, it had pockets and, you know, so we managed to straighten it out really nice, and we got enough fill in here that Ted will only have to do a finish coat on this and it'll be gorgeous.
What I always like to do with the adobe walls is come in and shave all the corners down, make them nice radiuses. Then when it's time to apply the mud, I have the option of either putting a real hard edge back on or staying with a nice smooth radius. Then it's just a matter of starting to put the mud on and just get it stuck to the stucco lath. You just start working back and forth. You add a little mud here, take a little off there, you play with the corners. You look at the wall as kind of a big overall mass. Look at it as a sculpture. And this is like working with chocolate frosting. It's got this great texture. You push hard with a trowel and you can get it perfectly smooth. It's like pushing a clay block around. And you have tremendous amount of latitude in the shape. You start looking for slight imperfections and accentuating those, because with an adobe wall, you do not want it to be perfectly plumb. You don't want it to have perfectly hard edges. You want this to look like that it's been worked by hand, that it has some expression in it. And keep working back and forth until you get a shape that starts to feel right. We're not having to go with a real thick coat. We just want it thick enough to cover the stucco lath and seal in the adobe, since we're putting mud onto mud. 1/2 inch, 3/4 of an inch is perfectly thick enough in this case.
Inside, I recommend everybody go for mud. There's different colors. You can fix it yourself, repair it yourself, do it yourself. It's a beautiful organic matter. When it gets on you, there's no lime, there's no cement, drying out your skin, cracking, burning your eyes. Mud, you can be covered in it, wash it out. You can work on it for 3 days on the inside while it's still wet. So those are bonuses about the mud.
All of the major construction is now complete. Finish work will prepare the home for the final inspection. Tile will be installed, sinks will be placed and plumbed, and the floors will be stained and sealed.
It's the final push to complete the house. By this time, the fatigue of such a long endeavor is really starting to set in. And what keeps going through my mind every day when I arrive at the construction site is, I am so glad I built such a small house.
Beautiful. A little high here for some reason.
Otherwise, I'd be working on this thing for 10 years. On this wall, we experimented with an alternative to standard sheetrock. Reed mats, which are sold as sunshades in home supply stores, were nailed directly to the stud wall. This material has low embodied energy in that it was grown, like any living plant, with sunlight. The mat acted as a lath, and mud was then applied in 2 coats to build it up to a thickness of a little more than an inch. The wet mud grips the mat and dries to a very hard surface. A 1/4 inch skim coat of gypsum plaster was then applied directly to the dry mud. The wall is remarkably strong and crack-free, and I have a feeling this technique will certainly find its way into future projects of mine. In the bathroom, colored gypsum plaster was applied to a base coat of cement stucco, and on the plumbing walls onto sheetrock. By using a pigmented gypsum plaster directly on the wall, we avoided the need for any paint. Only non-VOC paint was used throughout the house. Non-VOC paint means that it does not contain any volatile organic compounds. VOCs can be both toxic and also contribute to air pollution. The paint was locally available, reasonably priced, and had practically no smell during application. It adhered to the surfaces very well and looked as good as any other paint product that I've ever used. For wood floors, we use shellac, and shellac is a non-toxic product that is used, among other things, to coat pills and other food products. Shellac is a great substitute for varnishes that can contain toxic substances. Next, we acid stained the concrete floors. In addition to making the concrete look great, the darker color will help the floor collect solar energy. This acid is specifically formulated for coloring concrete after it has cured. Since it is acid-based, you must protect yourself properly. The diluted acid mixture is sprayed on using a simple garden sprayer. We approach this like a watercolor painting, allowing 3 or 4 different colors to run together. The longer it takes the floor to dry where the acid was applied, the darker the color. So we threw all sorts of junk on it to make it dry unevenly and therefore give a rich, stone-like texture to the concrete. It looked like the house had become a dump. I mean, we used straw, plastic bags, old carpet, newspaper, even leaves. 2 coats were used to give the desired depth. The residue is then washed off with a garden hose. It was a great material to use, except for one problem. It came to my attention over a year after completing the house that there is concern that the wash-off from acid staining should be treated as a hazardous waste due to materials used in the product. Because of this, the do-it-yourselfer has to evaluate the added complexity of dealing with an environmental waste disposal problem. In hindsight, adding powdered pigment to the concrete as it was being mixed would have been an environmentally sound alternative.
In order to define 2 distinct living areas in one space, part of the floor in this section of the house is raised, a technique often found in Japanese design. The raised section also provides a valuable storage area underneath the floor.
The raised platform is made up of a 2x6 frame. It was then sheeted with 1/2 inch thick plywood and then followed by 3/4 inch thick recycled oak that was obtained from a salvage yard. Recycled oak was chosen for its high durability and good looks. Two floor panels lift up to gain access to the storage area underneath. Where maximum durability was needed in a wall finish, a 1/4 inch skim coat of gypsum plaster was applied instead of mud. Gypsum works well in kitchens and bathrooms where there's a lot of water around. We also tried it on the west wall of the living room so that a side-by-side comparison could be made with white mud, which we would apply later on. Working with gypsum plaster is a race against the clock. The material must be applied and smooth before the plaster sets. There will be no breaks or resting until the entire wall is completed. At 8:19 that evening, the wall is finally complete.
Well, the kitchen's at a really neat transitional part now because I'm getting to decide all the finish details for the cabinets. When I first designed these, I was kind of thinking we just kind of put together a very simple plywood and 2x support, fairly beefy support for the concrete countertops. Now we have to decide how to finish it out. And as a test, I thought with the roughness of the whole house and that handmade look, maybe it would work just to coat this with a stain, which I've done a test of here, and see how that looks. And actually, I think it kind of ties in with everything. So for now, I'm going to leave it that way. And if in the future I decide I don't like it, it'll be really easy to change. Some other things I've done here. This was a metal and wooden drawer unit that I purchased and thought I would use it somewhere in the house, but didn't really have a particular spot for it. And so I just screwed it into the plywood. I actually kind of like the way it looks with this metal trim. It picks up with the metal stove I have. Here, I've got the wooden shelves, again made by 2x4s and 2x6s. Much of it scrap lumber that we glued together. In addition, gives a real nice stout looking shelf that's not going to warp. Up above that, I've installed a drawer filled with tools right now. Just a very simple drawer. This again will be stained green like the rest of the cabinets. Back here, more shelves made out of 2x. And these shelves, as you notice, have been spaced so these baskets fit right in underneath. And the purpose of this is that this is going to do away with the need of building cupboard shelves and additional drawers. Up here, we've roughed in the shelves. Again, they're made by 2x glued together, and we've fastened them to metal brackets that are screwed into 2x that are in the wall that we put in as cross braces specifically for the purpose of holding shelves. One kind of nice thing I like here is it needed some extra rigidity on the corners, and I've affixed it with some copper fittings here that pull it into the shelf. I think this will look real nice with the bamboo. Again, it's getting back to natural materials. It's serving a function, and it has a nice look that works with the wood.
The tile used in the kitchen and bathrooms was left over from the construction of another home, so the design of how the tile was to be laid out was therefore based on what was available.
Applying the last coat of mud will be one of the final steps in completing the house.
Here's the gypsum plaster that's white, and It's quite beautiful. This is a clay plaster. Clay-based, kaolin. It comes from Georgia. You can also find it in northern New Mexico. You can find it virtually anywhere in the country. And so it's an excellent alternative. People are used to having white walls or lighter colored walls. And this is all earth, sand, and straw. So it's a good alternative. Here's the regular mud from this area. It's the color that people usually assume a mud plaster is. And here's the kaolin-based clay plaster, also a mud plaster. And you can see the difference between the two. They're pretty dramatic. And you can even mix the two if you want a buff or a creamier color on the white. You can add a little bit of the brown. This is a stationary weed whacker or a garden mulcher, and I'm just going to connect the garbage bag to it, and the straw will go through this into the bag, and this will be our first chop through. Then we'll take it out and put it through again for the fine straw that we need for the finished plasters. The straw really needs to be good, clean straw, and you can see we've got some of that here, and we also have some mold that's starting up, that this has gotten wet and it's molded, and we really don't want that in the finished plaster because you can get moldy finished plaster, and that's a real drag. So we're going to start with good, clean straw, and we've got a bale down here. There's one end that's moldy, so I'm going to avoid that, but the rest of it looks really good. And I'll turn this on. Now, we've got some coarse ground straw here. Okay, come on. There we go. And you can see the consistency there. It's still got some pretty big chunks in it, so we're going to put this through again and come up with another finer version of this. Okay, we're starting with round 2 here. Okay, let's take a look at what we've got here. Oh yeah, it's a much finer straw that will really look nice in the finished plasters. Good, so we're ready to go here with straw. We're ready to start talking about the materials. Here we've got 60 grit silica sand, white silica sand. You can use a 70, you can use a 90, you can even use a 30. And if color is important to you, if you want to get a really good clean color, you want to make sure that you have a really good white sand. And this is a beautiful white. Sometimes it's hard to find this. You can also window screen regular mortar sand, and that will work perfectly well. You won't get as fine a polish on your finished plasters, but it works perfectly well. And here we've got a white kaolin. This is a pottery clay. You can buy it at any pottery store. The kind we've got here is called Tile 6, but you can also use an EPK or a DB float. And again, the thing you want to watch for is just that it's white and that it's kaolin. Kaolin doesn't expand and contract a whole lot, so it also doesn't crack a whole lot. And that's really great for a finished plaster. Makes it very easy. And we'll also be adding a few handfuls of the double chopped straw, which is nice and finely cut. So we'll put in a few handfuls of that. And our last ingredient, let's bring this down here, wheat paste, which have gone in the other plaster. It's a good binder, good adhesive strength for the wall, makes it not dust, which is really important. Finished plasters or any kind of plaster can be really dusty, and you really want to avoid that. So I think we're set for materials, and we can start loading into the mixer. We're going to use about 60% sand and 40% clay with some straw and the flour paste thrown in. You can go 1-to-1 for the sand and the clay, but we're going to go with a little bit higher sand content on this. So when I'm doing finished plasters, I like to use buckets to measure instead of shovels. because I can get a really accurate measurement. And when I'm working with color, that's really important. So, now we're going to add the clay. And again, you want to be pretty careful with your measuring here. Make sure they're nice full buckets. We're going to add to that 1 bucket of straw. You can add more. You don't have to add any at all, but it does add a really beautiful texture to it. So we're going to add that 1 bucket. Okay, and then we have flour paste. And we're adding about, this looks like about 1.5 cups, maybe 2 cups here. And this is, you could again add more. Some clays don't like flour paste at all, so sometimes you can't add any. It'll drag your trowel all over the place, but this is what we're using on this recipe. Okay, and we're ready to dry mix. So this mixer is really full of a lot of dry stuff, and when we add water, it will seem to just shrink down. But at this point, it's going to kick up a lot of dry stuff, dry powder, if we start turning it on. So this is the perfect tool for this job. It helps keep all of that dry material inside. Basically, you want to make sure all of the dry ingredients in the back that tend to sink there, the sand, is all mixed up with the rest of the materials. Now that we've got our dry mix ready, we'll start adding water. And the best way to do that is with the hose. A lot of people would like to know, well, how many buckets of water? And that will always shift a little bit. It's better to just understand the consistency that you're looking for, and then you can get that every time. While this is mixing and it's still fairly dry, I'll just keep the hose on full. And then once we start getting to a place where it looks, oh, you can see it shifting there. It's turning into little balls. And this is the point where it's easy to add too much water. So a little bit at a time is best. We're looking for something about the consistency of chocolate mousse, believe it or not. Okay, so let's check the consistency here. Ooh, it's lovely. You can tell it's pretty light. I think I want it a little bit wetter. But you know, if you're not sure, the best thing to do, and I do this a lot, is just to go throw some on the wall and see how it trowels out. Okay, so we're going to put a little test batch of our finished plaster on the wall. And I usually do a bunch of test batches, both to check the color and to check the texture and how good it stands up when I'm rubbing it and make sure it's good and solid. And the first thing I'm going to do is spray down the wall. And I always wet down the previous coat before I put on a fresh coat. It helps it bind the next layer to it. And so I really prefer the wet wall to work on. And then I'm just going to take a bit of this. Ooh, that's lovely. It goes on beautifully. It feels like icing a cake or something. And we actually do have a fair amount of straw that you can see in there. We'll have to buff it in order to actually see it. The plaster's all mixed and we're ready to put it on the walls. There were a few things we needed to do first with the wall. Masking is one of them. We cleaned off all of our edges and masked it down so that we'll get a nice sharp edge. And so we're ready to put the plaster on the walls now. So have all of your plaster ready that you'll need for this wall before you begin the wall. So you're just ready to blast it out there and you don't have to worry about running out of plaster. I'm going to start up at the top on the far edge of the wall. I'm using a plant sprayer to spray down the wall so that I don't get a whole lot of water over everything else. First, I'm just going to get some mud on the wall, and then I'll come back and smooth it over. And it's just good to come from different directions, really work the plaster into the wall, and watch those seams. And then I will leave some trowel marks in here, and I'll leave some texture in here, and I'll come back with the plastic yogurt lid and really smooth it down nice and beautiful. Yeah. So I'm grabbing just a little bit of plaster on my yogurt lid and running it down the corner with real light pressure, and it just makes a beautiful smooth round that I couldn't possibly get without that yogurt lid. Also on this outside corner, the yogurt lid is also good for creating, again, a smooth round. Okay, now that we're almost have enough plaster on the wall, we can start smoothing it out. So I've just wet this piece of plastic down a little bit, and then I'm going to drag it along the top. Let's see if I can get this right. It takes a little, there we go. That's starting to look good. But you know, you can see, this is not a curve you could do with a trowel. It just would be impossible to get all of those different angles looking right. And with the plastic, you really get a nice round curve. You know a wall is ready to buff when it's not tacky anymore, still wet, but not tacky. So now I'm starting to buff a little bit harder, and it's really using more pressure, and it's sealing up all the pores in the wall so that it becomes really smooth and very stable. And at this stage you can press really hard, and some stuff will come out and some stuff won't, but it's always a surprise to know what'll end up looking nicer. It definitely makes the wall feel more smooth the more you buff it. So we've got the masking off, all the plaster is on and buffed, and we just have a little bit of cleanup to do here along the bottom and the top, and the wall is looking beautiful.
The mud we're using for the final finish coat of mud plastering is a lot soupier than it was for the initial coats. And this allows it to go on a lot smoother since we're only putting it on about 1/4 inch thick. I'm bringing the thickness of the mud just about to the same thickness as the stucco down below. I'm filling in the gap that was there. For the bullnose corners, I'm just lightly loading the side of the trowel, quickly putting it in and then throwing it across the curve.
In contrast to the fine detail work on the interior walls, the exterior mud plastering is done with broad strokes, using only a pool trowel.
It's best to have at least 2 people at this stage, one applying the mud and the other smoothing it out. Long strokes are used from multiple directions. By the time you get to the final coat, you're very proficient at applying mud.
Again, as it starts to dry up a little bit, easy to smooth out, so you come back.
As the mud sets, I continue to work it with a trowel and apply quite a bit of pressure, working out all of the trowel marks. And you continue to work it until it meets the aesthetic that you're looking for. As you can see here, as the mud dries, it becomes lighter in color.
All the fine detail work is done. and the last coat of mud has been applied. The house is finished.
I really love the way this home turned out. It just has this great feeling to it that you can't convey with pictures or video or anything else. It just has an essence to it that feels so comfortable. I think aesthetics needs to be put into the forefront of green building design. Whether you're designing a single-family residence or an office building, the aesthetics will give the immediate feeling as to whether the entire structure is working or not. This becomes part of the form and function, or how well the building serves its occupants. If a building is going to last a long time, it should look good and make for a pleasant living and working environment.
I have rocks in my floor. I use rocks for my steps. I want things to last. I want the outside to be inside. I want to be able to walk through my door with lumber and hit the door jamb and put a nick in it and go, oh, isn't that nice? You know? Change the whole attitude about living in your dwelling. The dwelling is an organism that you should enjoy every minute and not worry about what you did to it wrong.
We are rapidly destroying a lot of our natural environment, and if we're going to do that, we need to make sure that what we build in its place will be well designed, aesthetically pleasing, and highly functional. In the past, it was never thought to really super insulate a building because why bother? You just put in a larger air conditioning system and just blast that hot air out. This is changing.
In this house, in the peak of summer, it might be 100 degrees outside at 3 in the afternoon. This house is generating over 900 watts of electricity, and basically the only thing running inside the house is the refrigerator that comes on and off occasionally like any refrigerator. There's no air conditioning system, so actually at peak demand, when the house down the street has its air conditioning running full blast just to keep the house comfortable inside and using its maximum amount of electricity late in the afternoon, this house is using an absolute minimal amount of electricity and generating its maximum amount of electricity.
And the best part is, you can have this kind of efficiency with a house that is also a really great place to live in. It's a hybrid house, which means that you get the best of both worlds. The aesthetics of using green and traditional materials combined with high technology for efficiency and clean energy generation. And how can you do better than that?
The purpose of building this home was to see what was possible when designing with a clean slate, free from pre-existing rules and precepts. What if we could design a house that could absorb sunlight, and this would keep it warm in the winter? What if the roof generated more than enough electricity to run every appliance in the house? What if we took advantage of the cool night air to keep the home comfortable during the hot days of summer? What if the insulation material we used grew in a field and, when stacked like oversized blocks, made beautiful thick walls with a minimal use of wood? What if a durable wall plaster could be dug out of the ground and then applied in a rainbow of colors without the need for paint? And what if these materials were easy to work with and naturally gave way to elegant forms and textures? This home was built by utilizing the best of all available materials and by making decisions based on getting the most out of form and function. It was designed by thinking about what was truly needed and, when necessary, discarding conventional building systems in favor of more innovative solutions. Creating this house was an attempt to move closer to how our planet works. Like nature itself, this is design with cause and effect in mind. This is building with awareness. For more information on alternative building, please visit www.buildingwithawareness.com.